So let's finish this one up. FB star is F sub B was the 2400. And then we put each of the C's in here, 1.15, and the rest were ones. All right, and you get 2760 psi. And in the C sub L equation, the lateral stability equation, we have a ratio in there over and over again. It's this ratio. So let's go ahead and calculate that. That's the 622 over 2760. Did I say 622? 6,226. And you get 2.3. So now I go back. Whoa. Now I go back and put everything into that C sub L equation. 1.2.1 plus 2.3 over 1.9 minus the square root quantity 1 plus 2.3 over 1.9. Probably have simplified that one out. That quantity squared minus 2.3 over 0.95. And I get 0.97, so pretty darn close to 1. C sub L is equal to 0.97, and that's greater than C sub B, which was 0.80. So we use the lesser one. So after all that work to get C sub L, C sub B actually controls. It's the smaller. So we go back and we get, all this was to get that coefficient, these two coefficients, and you take the smaller one, F sub B x prime is now 2400 psi 1.15. I've got, I use the 0.8, and then everything else was ones. And I get 2208 psi. All right, so now I've got that value, little f sub b. What do I need? Our demand is 288 kip feet, 12 inches per foot, 1,000 pounds per kip, over 1582 inches cubed. And now I get 2185 psi. I know that I need little fb, the demand, to be less than what is applied. And I get 2185 is less than 2208. So cutting it somewhat close here, but it's okay for flexure. Now, if you recall, this is always the trick, is keeping track of your assumptions. We need to check the dead load assumption and make sure, so it assumed a dead load when it gave us the loads, a self weight of 100 PLF. The self weight of our glue lamb is 253.1 inches squared was my area. If I convert that to feet, 1.76 square feet. They didn't give us a species, but we're going to assume it was the same as last time, the one we did with Douglas fir larch. So that wasn't stated in the problem. We get to choose, so we'll choose Douglas fir larch. Depends on where you are. This is not southern pine, but other than that, we can look at what we want. And as you recall, the reason I chose that is because we just did that one, and it was 35 pounds per cubic foot, which will give us 61 0.6 pounds per linear foot. It's less than 100. Okay. It's not that close to 100. But we're going to call it close enough. If this was one beam, and the glue lambs are typically going to be one beam or so. If this was one beam and I'm not doing a ton of them, it's probably close enough. Also, we weren't way over designed here. So by the time we take 40-ish pounds per linear foot, put that in the loads that we have with a 288 kip foot type load, that's not going to be anything. So it's probably not super conservative when you consider how little piece of that is for the load. Okay. So our assumption didn't cause any problems here. And let's wrap this one up with our shear and deflection checks. Okay. Again, in the x direction, f sub vx equals 3v over 20, or sorry, 2vd, 3 times 1,000 pounds per linear foot times 48 feet divided by 2, right, the shear piece, 2, 6.75, there's WL over 2 for shear, 37.5 is 142 PSI. If we get close on shear, we'll go back and calculate the shear just over from the support, but typically we are not going to need to do that. F Vx prime. We from our table in chapter 5, since we're in glue lambs, these are the coefficients we use. CD, CM, CT, and C sub VR. That's radial. Equals 265 if we look that one up. PSI, this is 1.15, 1, 1, 1. So each of those are 1, and I get 305 PSI. Little Vx less than big F sub Vx. I get 142 is much less than 305 PSI. And as usual, shear is not an issue. When we start looking at notches and stuff, that's a little bit different, but the general shear capacity of the beam is fine. And let's finish up with deflection. Our deflection equation is the usual because it's simply supported 5WL to the 4th over 384 EI. If you substitute in let's hold on for just a second here. We need E, and in this case it's going to be E prime, which is E times C sub n, C sub t. Our E value that we use for deflections for this is 1.8 million. Those two C values we've looked at several times are just 1, so 1.8 million is our E value. If I use W total load, I will get a delta of 2.24 inches. The requirements that they told us to use were those at IBC in the table, which in this case is L over 180. So L over 180 is going to give me 3.2 inches. So 2.24 actual less than the 3.2 allowable. Okay for a delta total. And then we need to do delta due to this live load, which in this case is the snow load. And that's L over 240. and that will give me 1.68 maximum. Just for the snow in this case. And that needs to be less than, oh, sorry, I didn't go through the whole thing. So if I go through that same calculation for the snow loads, I get 1.68 is the actual calculation. Skipped a step there. L over 240, which makes a lot more sense, is 2.4 inches. And the actual calculated one, if I go through my 5W just to snow, L to the fourth over 384 EI, that gives me 1.68. So that is less than the 2.4. Delta snow is also okay. Now, we may not want, so both of these meet the requirements, but 3 inches of deflection and 1.6 inches just from snow load. So, almost a 2-inch deflection on your roof beam just because of snow load. Although that's probably full snow load is a bit much. So one of the things we could do, these are fairly high, fairly large deflections. It's because it's a large, long beam. We aren't looking at any specifics. So let's say this is a beam. It's got some sensitive items on it, plaster or something that might crack. I might have a different requirement here. Could camber. At 1.5 delta dead load. Okay. And if I did just the dead load calculation, that guy was actually 0.8 inches is what I get there. So I could camber 1.2 inches, so like this. That 1.2 would help counterbalance these larger deflections, so I'd get a actual deflection under total load of only 2 inches instead of 3.2 inches. So if you're designing this, I mean, it's one thing when we're doing these in class, but you might decide, hey, I'm going to camber this. They suggest this with these larger spans so that I don't get such a big deflected load or a deflected value. All right, that's it for this glulam bead. So it's a little bit long just because we had to go through that C sub L piece, the lateral stability item. But otherwise, reasonably straightforward. It's not that different from the sawn lumber, except for you use different tables, and you just need to pay attention to which direction your laminates are in. So this wraps up the glulam example.